thanks for coming to our podcast. And I guess today we want to talk about the what are you guys building at the Ground Control Robotics. I know
Yeah.
you guys are building the centipede-inspired robots that can move through different environments, such as like traditional robots are struggling at, like farms, crawl spaces, industrial facilities, and disaster zones.
Yeah.
So I think my first question to you would be for people hearing about ground control robotics for the first time, what problem are you trying to solve?
Yeah, we break it up into what we call the three Ds, dangerous, dull, and dirty environments. Although we're about to add a fourth D, I think disgusting is a fourth D. Basically, environments and regimes of locomotor where we need locomotor capabilities, which no other robots can effectively go into right now, and which whose principles we've discovered out of 20 years of my lab at Georgia Tech. I should just can I take like a minute backstory just to kind of
Of course, yeah.
frame some of this? Yeah. So I'm a PhD physicist and have been working on what we call physics of living systems, biological physics now for, like I said, 2 decades. And the little niche I discovered about 20 years ago was that most physicists were working on cells and molecules, great, and applying physics to that kind of biology. And we realized that there was a very interesting application of physics to biological problems at the organismal scale. And one of the important problems is movement. And one of the important movement environments is which had been underappreciated is terrestrial environments. We tend to think of terrestrial environments as flat paved roads. I see in the background your the Golden Gate Bridge, right, with the nice flat paved roads. And we have robots, autonomous vehicles, which can drive pretty well over flat paved roads. When the roads or the environment gets a little more complicated, this is where the rise of the quadrupeds and the humanoids has sort of come into, when you want to sort of step over something or move in a slightly more complicated environment, having a long-legged locomotor is a good thing. And in fact, the genesis of those robots goes back to the 80s and actually 70s and 80s and basic discoveries in biology of organisms running over flat ground. Biologists discovered that organisms tend to walk in a certain way across a variety of scales and run in a certain way across a variety of scales. And in fact, some of that thinking is what led folks like Mark Graber to come up with these kind of bouncing robots, which have revolutionized the kind of mobility in synthetic systems. Uh, what folks hadn't appreciated so much was that the terrestrial world is actually, in your background, is a great example. If you look next to your picture of the Golden Gate Bridge, you see a lot of slopey, rocky stuff with grass, and that's where lots of organisms live, and not many robots or any thus far can do particularly well for sustained times in these. And it turns out that the lots of organisms living there, people hadn't really paid attention to how, for example, a little lizard can move around in loose material like sand, or a cockroach can climb up, kind of rough tree bark, or spiders can run over sort of bumpy ground. So back 25 years ago, I did a postdoc on the eastern side of the bridge there at UC Berkeley with a guy named Bob Full, who's one of the pioneers of organismal biomechanics of the kind of bouncy running systems. And we came to the realization that a lot of these animals that no one had paid attention to, inhabiting a lot of these environments that nobody paid attention to, were really ripe for study, and study from the point of view of physicists. That's my kind of academic backstory. At the same time, we as academics were working on federally funded research that was largely defense funded via Army Research Lab and some DARPA. The interest was to be inspired. The engineers were going to be inspired by the biological discoveries and make better robots. And in fact, I would say the Spot robot, for example, came out of that program, by some accounting. Uh, what I realized very early observing the engineers and talking to them is that To me, they were making models of the organisms. They didn't think of them like that. They thought of them as, again, bio-inspired artifacts or products. I, in my physics head, said, boy, because in physics, we love to make models. We love to pretend the world is simple. Say, okay, I'm going to study a lizard swimming. I'm going to pretend it's either a mathematical line wiggling or maybe a computer simulation. But hey, why not make a robot, which basically then you don't have to simulate the environment, where you can do the same things you do in a model, vary parameters, and test biological hypotheses. So when I got to Georgia Tech in physics, 2007, I wanted to implement this program. So I was working with engineers who would give me robots. I would treat them as models. In fact, at the point where, and this is the critical bit, I didn't care whether the robot did well or did poorly. I wasn't in it for making cool YouTube videos. I was in it to try to really understand, how does the robot fail when it moves on a loose material, when it has to get stuck in a confined environment. And so we did that. That went slow until 3D printers came online, and went slow until waves of high school students who had come up being trained by these incredible programs like FIRST Robotics came to Georgia Tech. And there, my lab became infested with 3D printers, with low-cost microcontrollers, with low-cost but powerful motors, and brilliant students. And from there, it's just sort of exploded. And it exploded in such a way that we decided we needed a name. And my colleague, Howie Joseph, who's a pioneer in limbless robots, and I came up with a term called robophysics, which sort of described this interaction of physics and robotics as a way less about making cool demo videos and more about really discovering the fundamental principles by which these dynamical systems can interact effectively or poorly with their environments. That's my next part of the academic backstory. And to finish this up, a few years back, a collaborator of mine and colleague and dear friend, who was not only a true scientist, but a serial entrepreneur, he said, you know, your robophysical models are starting to look a lot more like real robots than they are just laboratory curiosities. And I wasn't interested because in physics, you know, you may or may not know this, the more practical we are, the more there's a snobism that you're not doing real physics. But I sort of held my nose and put that to the side. And we started talking to he happened to have made his big score in agriculture, not in robotics, but in agriculture. We started talking to some of his investor friends. They said, ooh, this sounds like an interesting idea. Imagine you have a bunch of robots running around a crop field looking for weeds, looking for problems in the field 24/7, and so on and so forth. So we started the company, Ground Control Robotics, with that. Sadly, a couple years later, he passed away. And we sort of were with a robot that you might say is inspired by a centipede, but we thought of it more as a model of a centipede. It was a big, clunky body with lots of pointy legs. It wasn't particularly capable. We had some idea that it could be capable, but the engineering wasn't there yet. And we had agriculture, which we then realized required real full autonomy. You know, you sort of needed Roombas for the outdoors, and we didn't have those yet. And then we hit upon two things. The first was we published a paper in the journal Science, which is the premier scientific venue for high-profile ideas, in which we discovered that these multi-legged elongate systems have very nice properties, emergent capabilities, such that basically, if in open loop, if I put enough segments with enough little, even rudimentary limbs making and breaking contact with the ground, and I wiggle my body in the right way, I can guarantee locomotion performance. Or another way of saying it, based on the analogy we made in that paper, is that if I want to transmit matter from A to B, I simply can code it with enough redundancy, spatial redundancy, and mathematically that will guarantee on a noisy landscape, on a noisy channel, I will make it from A to B with a probability approaching 1 as the number of segments approaches infinity. Some mathematical statement. If that sounds like information theory, that was exactly what inspired it. Communication theory, and we've subsequently gone on a whole on a whole adventure, sort of mapping ideas from signal transmission over noisy channels to matter transmission. What that said was that we could guarantee this robot could go over bumpy, noisy terrain. Okay, that was point one. Point two is that the agriculture vertical seemed hard. The go-to-market was longer because we needed full autonomy. We happened by random chance to find somebody who was in the pest control industry. Now, Atlanta, Georgia, where I'm headquartered, where Georgia Tech is and where Ground Control Robotics headquarters, happens to have a whole lot of pest control companies and some of the largest in the world. And we met somebody, and they put us in contact with a guy who edited Pest Control Technology magazine, the premier trade magazine. And they heard about our robot and wrote a very nice piece basically saying, boy, suppose you could have a robot that could go anywhere in any noisy, nasty, stochastic environment. What kind of jobs and job opportunities and reduction of costs could that lead to? And that is now where we're focused in pest control, selling our robots for application in crawl spaces, attics, and other places where pest technicians either can't go, would like not to go, or it's cost prohibitive to go. That's my 1 bit word a minute. That's my kind of 5-minute preamble.
Oh, that's great, Dan. Thank you so much. I mean, you superseded a lot of my questions, but that was a great answer, honestly. I mean, like you said, you had this great opportunity to play around in academia research, and like all the best innovations come from academia research because, like, this is where it all starts, right? Before it goes
Nice.
commercial. Any
Nice to
phase,
hear
right?
you say that. Nice to hear you say that. And if I could do anything in my current role as CEO and still Georgia Tech professor, it's to emphasize just how important funding basic academic research is. It is the driver.
Yeah, of course. And let me ask you a question. So, compared to other robots, like what advantages does your, I would say, segmented body provide compared to like wheeled robots or humanoids?
No, it's really interesting. And I'll say that one of the fun things is we're just learning what those are, in the sense is that, evolutionarily, there's a whole lot of, there's been a diversification of body forms and shapes and control systems over the, hundreds of millions, billions of years of life on Earth. Not every organism looks like an upright biped. Not every organism looks like a quadruped. In fact, the majority do not, obviously. And so we're really learning what you get. I will say that if you want to go into a confined space where, let's say, the dimension you're trying to fit through is small, well, you have to make a small robot. The problem with making a small robot with wheels is that, as you know, drive an RC car, everything becomes an impediment and obstacle. You can't step over things. So you say, okay, well, maybe I can make a suspension system. That gets you some part of the way there. They say, okay, let me do better. Let me make a long-legged quadruped. There used to be something called little dog. The problem is, and we discovered in our science paper, is that you can get very lucky if you get the right footsteps and you get to the right and get through a confined space. But oftentimes you get very unlucky. You miss a footstep. You can't climb over something. You can't kind of bend around a corner. And so you're limited. And they say, well, how to improve that? Well, you can't make it bigger because you're still trying to get in that confined space. The trick we discovered is that you make it longer. You repeat those modules. And what that allows you to do is, one, have this redundancy of interaction that I talked about. But two, it turns out, and this is a mind-blowing fact, the one big fact we've learned, I guess, is that the animals we study are effectively operating in a world where inertia doesn't matter. When you and I run, or a dog robot trots so gracefully, or a cheetah robot, we're relying on kind of inertia to carry us from step to step. In the world of centipedes, centipede robots, lizards, snakes, inertia doesn't matter. Basically, the only thing that matters, history doesn't matter, is your current shape and your shape you're going to next. That opens up a suite of theoretical tools which allow us to predict in different environments how a change of body shape will lead to propulsion. So the other feature of having an elongate system is that you inherit snake-like properties, worm-like properties, which then allow you to bend your body to, crudely speaking, manage environmental forces to to kind of effectively propel. And what it does then is it takes the robot from kind of our traditional human engineering of box with appendages, which is basically what they are, to something where the entire structure is both part of the entire structure is generating propulsion. In fact, I was just talking to some folks last night, and one guy said, "Hey, where's the engine on your robot? Is it at the front?" And it struck me, I had never thought of it like that. Because if you look at this thing, it looks like a train. And you know, with a train, we have an engine and it pulls a lot of stuff. Nope. Every part of the robot is an actuator and potentially a sensor. And that then allows you to curl your body in interesting shapes. And because we understand how shape changes in these microscopic organisms work, and our robots map from the microscopic to the macroscopic, we understand how particular changes of shape lead to propulsion in the large scale. So it's quite a beautiful set of things that have conspired here.
Okay, no, that's a great answer. Um, I know you have this saying on your website, swimming through terrain kind of concept.
Yeah.
I mean, it's
Yeah.
fascinating idea because like most robots try to avoid obstacles, and you see a lot of those funny videos on TikTok and YouTube where those delivery robots got stuck, people trying to help them, like to like go over the curb and stuff like that, and you seems to use that right in a different direction. So can you kind of elaborate on that a little bit more?
That's a terrific question. In fact, that's exactly it. We think of these things, we call them terrestrial swimmers. And if you really want to be academic and fancy, it's stochastic terrestrial swimmers, meaning that when a worm swims in a fluid at low Reynolds number, meaning very viscous, or when an eel swims, you're immersed in the medium at all times. You're using the medium to prepare. When a bird flies, you're using the medium. We tend to use the medium in kind of almost secondarily. It just can't we just can't sink through and we can't lose friction. Organisms like centipedes, snakes, lizards use the medium in more like a swimming. Every element of the body is pushing off the environment and experiencing dissipation from the environment. That's the swimming feature. You can swim in the plane, right? And that having the right kind of swimming with the right kind of redundancy allows you, if there's a bump in the ground, well, your leg kind of hits it, but the next leg is already there to go over it. If there's we'll say 2.5D, we're working on vertical climbing, but let's just say 2.5D where you have to go over a curb or a nasty divot. In Atlanta, we have a lot of potholes and our sidewalks are pretty disgusting on average near the Georgia Tech campus. You get a lot of bumps and holes. The robot sort of, bends its body and glides through those. And so it really is a frictional swimming as the better model. And so the paradigm shift is less the robot as kind of mildly coupled to its environment in this physics language, and now the robot is strongly coupled to its environment. And so you have to sort of think of the robot and the environment as part and parcel of the same thing.
Okay, that's great. And talking about like a real world applications,
Yeah.
where are the customers deploying these robots today?
Well, we are currently in a pilot program with the second largest pest control company in the world, and our beachhead that we've targeted is pest control, mainly because there are customers. There's a quick go to market, uh, and and it's basically environments that once you say it is pretty obvious. Like I don't want to go into a crawl space. It's filled with all sorts of gross stuff, including as we hear often, raccoons and their babies. And the worst thing to encounter in a crawl space, evidently, is a mother raccoon with her babies. And no technician wants to go in there. But those are the places you don't want to access, or maybe can't. Maybe the crawl space is too narrow. So a lot of the time, these poor guys have to dig out an extra, space to get in, or they're too old, we're told, to get in. So that's an obvious one. Attics are a very important source of needing to inspect. Right now, we're focused on inspection. We're not replacing the technician. We give them a robot and a joystick, and the joystick is like a drone controller with a camera. We have a 360 cam on there, and they can then go and inspect the various environments, attics, the far recesses of the attic where there may be rats nesting where there may be termite damage. You put a visible light camera and a thermal cam on, maybe a humidity sensor. One of the nice things about having a modular robot is you could just start, creating modules with different sensing elements. Okay, I want this module to have the humidity. I want this one to have more battery. I want this one to have the thermal cam. Off you go. And then there's things like drop ceilings. Suppose you want to inspect the ceilings of a building, which are false ceilings. Well, rather than putting up a ladder and inspecting, and I'm looking at my drop ceiling above my head, you send the robot up there and it just wanders around for a couple hours and records data, video data. The next stage for us is the interventional aspects. Take the robot and add applicators, let's say, add a tube where you can spray chemical, add rat trap depositors. The number of applications grows with every conversation, honestly.
Okay. I mean, that's a lot of applications for sure. And like you said, a lot of those hazardous spaces people don't want to go anymore.
And
You
I'll tell
know.
you, if you really want some excitement for your audience, if you're in Texas, in Grapevine, I think in October, I think it's in Grapevine, in October, there will be the largest pest control meeting of the world called Pest World 2026. And that's where our official launch will be taking place. We'll be in a
Oh,
booth at Pest
interesting.
World. For those who are in the area and want to see want to hear the craziest stories you'll ever hear about where robots can really help, that's where we'll be.
Interesting. So I understand right now, I guess the agriculture is your major opportunity, right, for the company. So I guess my question would be, could these robots eventually replace like pesticides or significantly reduce like the chemical use for the
Yeah.
farms?
Yeah, that was actually where the company started. That was the pitch. I would say that our beachhead right now is pest control and AEC, architecture, engineering, and construction, of which several other robot companies are doing. Field
Mhm.
AI, of course, is talking Boston Dynamics, and people want to put robots for inspecting and mapping, photogrammetry, and the like. Um, the agriculture is very interesting to me and very compelling. It it requires full autonomy. You need fleets of these robots, 24/7 recharging, running around. We're not there yet. That's what we're looking to kind of develop out in the next year or two. But there the pain is real. There, you have crop fields where there are plenty of crop fields. And again, looking at your background, the Bay Area, you go over to Napa, Sonoma, where they're hilly, rocky, craggy. You can't get a tractor up there. It's hard to get humans up there. Suppose you have robots that can basically go there. They can look for weeds. They can locally destroy the weed, intervene either with a, mechanical thing, or if the environment is suitable, a laser. Um, that's the kind of interventional. Even the surveying we've discovered has value. The ability to know what's going on your ranch, your 10-acre plot. Do I have an irrigation line which is dripping? Do I have the number of applications is pretty vast there too. And there are plenty of robots now operating in crop fields. They tend to be row crop. They tend to be relatively, flat, prepared environments. And the robots tend to be relatively high impact, meaning they're heavy. They compact the soil. One of the other nice things we latched onto very early on is that our robots are low impact. That weigh under 10 pounds. They don't disturb the soil, and they can get critically under canopy, where you can spot disease which might be starting
Mhm.
under the leaf, where you can't see it from. There's also then the interventional. You can spray. You could potentially, so there's a lot of interesting, and that's great, but it isn't practical at our level, the size of our company, to go after that market. So we're really focusing hard on the pest control as our beachhead to really kind of bootstrap ourselves up into big sales and then big revenue.
Okay. Oh, that's very interesting. And like you've been focused on a specific niche like farming. I mean, like you said, it's huge. It's a $1 billion industry, so you cannot go wrong with that.
Multi-billion. Yeah. I mean,
Yeah.
the TAMs for ag, I forget, or for pest control, it's pretty big. AC is even bigger. Of course, there's the defense play, right? Boy, would it be nice to have robots that could go around and demine a field
Yeah,
that are low cost that don't, but
save a lot of lives. Yeah,
save a
that's
lot of
definitely.
lives.
Yeah. Listen, let's switch gears a little bit. I guess, of course, we cannot go without AI because robots is just hardware, right? So, and everybody talks about AI today. So, how important is AI versus the mobility in your case?
Yeah, I don't see it as a versus. I'll tell you the interesting thing. So it's funny. I was just talking to some folks last night. You know, in my world, in my academic biomechanics meet robophysics world, we've been talking about embodiment, physical intelligence, mechanical intelligence, um, preflexive control for 30 years, right? Where the body has a brain, where the artificial intelligence comes in as much as in the compute as in the kind of mechanical compute. So I would say that artificial intelligence, and Rodney Brooks and visionaries have written all about this, Rayburn and others, the intelligence in the body is, as we're discovering, as important in these environments as the intelligence in the brain. One of the most interesting things about these robots we've developed is there's basically been no reinforcement learning, no millions of hours of training the robots in sim. One, you can't simulate many of the environments we're interested in. Try simulating a crawl space, good luck. But two, we think that this approach of physics meets robotics meets biology generates rapid understanding of what are the important critical physical interactions you need to understand. And they're not modelable, and the LLMs don't know about them yet. Maybe can't know about them yet because they do require intrinsic, interaction with the real world. So where we see our robots, what we've discovered is that our robots are open loop, and we have theory for this, very capable. Augmenting the open loop with simple but robust sensing of the right kind. And this is the critical bit, the sensing of the right kind. Do you need to LiDAR everything? Do you need to visual camera everything? Answer when you're in, leaf litter or that brush or that scraggly stuff that I'm staring over your right shoulder on your background is, probably pretty useless. We have a lot of cool video now of our robots running around and pretty nasty stuff where good luck identifying your next move from a camera image. So tactile information is important. Then integrating that to kind of behaviors which get you out of local traps is very valuable. Then what we're discovering is that you can bring on the AI, the more agentic style of thinking. And that's where I think the real value is going to bring. Now, don't get me wrong, we do simulate and we do, the RL dance to try to find better ways to coordinate the body and limbs. But the fact that we already have theory and principles gets us kind of short circuits a lot of that huge compute load that gives us then a predictability and a kind of robustness that doesn't degrade in different environments. It's pretty interesting. So we are ready to integrate the AI. And I'll tell you one other fact, which I just love. We've been studying now for 5 years or so a little worm called a C. elegans nematode worm, which has famously 301, 302 neurons. That's it, right? It's millimeter long, 100 microns diameter, and lives in the nastiest environments, rotten fruit, soil. It goes through everything. It goes through fluid, goes through solid, with 301 neurons, right? And it didn't require, a whole lot of digital simulation to now required, hundreds of millions of years of evolution. But that to me is a great example of if you get the body mechanics right, and I only talk about this because we've made a robo-physical model where we can basically reproduce the nematode behavior quite well in pretty diverse environments using a new kind of actuation, which is modeled on the organism. You can get a very capable robot for very minimal computational effort. And to me, that's a big win. And that's what our company is sort of based around.
Okay, listen, that's a great answer. And I guess the interesting question everybody's now curious nowadays, how autonomous are your robots today? Because a lot of them we know, like we see they're doing all these tricks and
Yeah,
they're
yeah, yeah.
jumping and doing all this, but then you see a person behind the curtain with the joystick,
Yeah,
right?
no, no. We are deliberately, I am not a I'm a physicist at heart, so I'm temperamentally unable to oversell. So maybe to my detriment. I will say that we are not autonomous yet, deliberately. One, because our customers don't want us to be autonomous yet. The technician wants a joystick to be able to send the robot. Now, over time, folks will say, hey, I don't want to have to control every action. Let me make the robot, be able to, go through a bunch of, waypoints and we are building that in on our kind of more skunkworks side. But again, we don't understand the principles by which they can really robustly happen. We're beginning to understand not the open loop, the open loop plus driver controlled uh, uh, behaviors, but we're still, I'd say, a couple of years away from the real autonomy. Now, if suddenly somebody deposits a large sum of money in my company bank account, that could be accelerated. But barring that, we're kind of going carefully and steadily to really making these things very robust in the hands of the technician. Like I said, though, the beautiful thing about the autonomy on these robots is that they're sort of pre-adapted for autonomy. That's a term in biology. It's a funny term. Basically, this mechanical intelligence, this physical intelligence they have, lends itself very well to the addition of the right sensor, leads to really remarkably looking autonomous behaviors. But so that's coming, and I see the path. But right now we're focusing on what the technicians want, which is basically hold that thing, okay, go in the attic, go in the crawl space, throw it out. That's what we're focusing on
Okay,
now.
that's great stuff. And a lot of conversation nowadays around the LLM models and how meaningful they are to the robotics development. In your particular case, do you think it's more about the foundation models or an actual LLMs?
Neither, neither,
Neither.
neither. We are, and again, I'm not against it uh, at all. I think the foundation models are interesting. I think the LLMs are great, and they help us, right? They help us code things. They help us, but you know, and maybe this is my physics. The real world is really hard to model, having now done it for many years, and simply photogrammetrically scanning visually doesn't give you the real physics of what's going on. Now, some of that physics may not be necessary, but right now, we're not finding a real need to go that approach. We're taking a different approach. We're really, like I said, we're putting the physics and physical AI. We're really going all in. And it's funny. We were we were attendees at Jeff Bezos's Mars event a couple months ago, and he got to drive the rope. We had a couple scuttles. Scuttles the name of our robot. He had a couple scuttles, and he and some other folks got to drive them around. And you could see that they saw that this is really a way to kind of accelerate robots into these kind of environments without needing. I mean, think about the amount of computation you're using to do relatively simple robotic tasks at this point. I think that we'll keep riding with this approach, layering in the tools when appropriate. The higher cognitive levels is how I'd like to think about it.
Yeah,
The body still has a lot of brain power to teach us.
of course. Well, I guess piggyback on that question, are we overestimating like humanoid robots and underestimating like specialized robots like you guys have?
Yeah, I would say that the humanoids are the specialized ones. If
Okay.
I take my biological hat, Homo sapien is a weird little, thing that's only been come to prominence in the last couple 100,000 years. Bipedalism, is not the rule. There's most of the world out there does not walk around upright on two legs. Now, there are plenty of environments, I think, where it's good to have humanoids, factories and this, and if you want them to wander around with us. But I would say our robots are the more gentlest robots, and those are kind of the funny, weird, human adapted robots. But I imagine a world where robot form and shape and diversity is as great as the natural world. And then the humanoids will be one interesting, component of that for sure. But there's a lot of when you have a hammer, everything looks like a nail, right? I think that's the humanoid mania right now. And the dogs as well have their role. But the average large organism on the planet has 6 legs, and it's kind of crawling around. The insects, the beetles, insects, myriapods, other kind of critters are quite numerous. Ants, for
Okay.
example. The other sort of thing I'll say, last bit I'll say, is that what I like about our platform and our thinking is that it feeds nicely into collaborative aspects, social robotics. You have groups of robots doing things. So it may be that you want a humanoid holding 3 scuttles and throwing them where it needs to go, or the scuttle riding on the back of a dog robot and going where it needs to go. You may need all those things, but I think that the amount of resources going into the humanoid robots relative to, I think, what folks, if they thought more creatively, could deploy their money, is quite interesting.
Okay. Well, that's a great answer. And let's say we fast forward like 5 years from now, because now everything even moves even faster, I guess, 3 years from now.
Yes.
What will
Yeah.
surprise people most about the robotics industry?
That's a great question. And it's one that those of us in robotics are thinking about, because some of us feel like that robotics has been kind of is playing second fiddle to the kind of, let's say, digital computational AI advances. Uh, and I think that if things go well and real resources can be brought to bear, real resources into both academia and industry, then I think in 5 years, my hope would be an explosion of robot shapes, body plans, the beginnings of new materials that can be used, new actuators, new skins that can be used to power and protect and control these robots. And in the absence of that, I suspect we will have relatively standard looking platforms, humanoids, maybe some dogs, which will look increasingly sophisticated in their capabilities. My bet would be, if I had to bet, and predictions hard, like Niels Bohr said, especially the future, my bet would be that they will still not be robust enough to be trusted around, let's say, the home.
Hmm. Yeah, of course. That's where this, I guess, cognitive perception or cognitive AI comes into play, right? And how they can actually read people's behavior and gestures and facial expressions and what's not, right?
Well, that's the one thing. I would worry more about the big robot with lots of metal parts, bashing into, my 13-year-old
Yeah.
old daughter or something like that, or hitting grandma. If you've ever had to deal with people who are cognitively or motor impaired, you got to be very, very careful. And I think that, that's probably still pretty far off.
Okay. Well, there's still there's always room for improvement, right?
Correct. Correct. I would champion, if I have to champion anything, uh, diversity of, open up the mind to more diverse platforms, less specialized platforms, more basic research to kind of unlock cool and creative principles.
Okay, that's a great answer. I guess my last question for you would be then, if everything goes great for ground control robotics, where do you see company in 10 years?
Again, predictions hard, especially in the future. I would like to be that company that's leading this kind of creative physics-based approach to robotics, where our platforms diversify in scale, tiny to big, shape, many-legged to amorphous sort of things, environments. Pest control is great. I want to go to space. I want to put these into, onto the moon, onto lava tubes. I want, you know, these robots, I believe that this system and the approach we've developed can lead to robots that really can go anywhere with the capabilities of organisms. That's my 10-year vision.
Listen, that's a great vision. Would love to see robots in that lunar and Mars base
Listen, I'm going to
whenever we
do it.
get there.
I'm going to do
Knock
it.
on wood. Yeah. Listen, Dan, thank you so much for this opportunity. It's been great, and yeah, I'm sure followers would love to hear about your company more in coming time. Thank you.
All right, Sergey, thanks so much, and appreciate your time.